one of my favorite theorems of the year. It's an important one. So if you remember from the first unit, we had the intermediate value theorem, and today we're going to talk about the mean value theorem. And typically I start this off in school with you guys, and we do a little extra credit game where I kind of give you guys an opportunity for extra credit. But of course that's not happening this year. So this is the game we usually play. I have this program on my computer, and it's actually outdated, and we're going to lose it soon, so I'm glad I can still at least show it to you guys. But before we do this, let's talk about what is the mean value theorem. So the mean value theorem states if f of x is continuous on the closed interval a to b, and f of x is differentiable on the open interval, because remember, you can't be differentiable at the endpoints, then there is a value c such that a is less than c, which is less than b, so c is in between the two of them, where the derivative, f prime of c, is equal to, what does that look like? F of b minus f of a over b minus a. That is the slope formula. So what does this mean? So let's break it down into some easier words to understand. So first of all, the function has to be continuous and it has to be differentiable. That's easy enough to understand. So the only way the mean value theorem is valid is if those two things are true. So if those two things are true, then there is some sort of value on the interval. So remember, the interval starts at a and ends at b. So there's some middle, there's a number in between a and b, where the derivative at that point, so that's the instantaneous rate of change, or the derivative, is equal to the slope between these 2 points, or the slope of the secant line. So what this is saying is there is some value on this continuous and differentiable function where the instantaneous rate of change is equal to the average rate of change. Okay, so I'm going to put that over here, average rate of change, because this is the slope formula is referred to as the average rate of change a lot, and you need to know what that means. So this is the instantaneous rate of change. I'm going to say rate of change. And then the slope formula is the average rate of change. So this is the slope of the tangent line. This is the slope of the secant line. So let's talk about what this means. So there's a point on this function where the slope of the secant line has to be equal to the slope of the tangent line. That's actually really cool and beautiful when you think about it. So let's go back and look at this, if I can find out of my 8,000 things that I have open here. So what this is saying is, so let's look at the secant line. So here's the secant line between a and b. What this is saying is because this function is continuous on the closed interval, right? There's no breaks in that graph, and it's differentiable on the open interval, is that there must be some point on this function where the derivative is equal to the slope of the secant line. And that makes so much sense, because this is the average rate of change between these 2 points, and then obviously in between that we're above it, we're below it, but we've eventually at some point we have to be equal to that average rate of change because the function is continuous. If the function isn't continuous, then it doesn't really apply. But because it is, the average has to eventually equal the instantaneous, and this is so unbelievably cool. So let's take a look at this. I'm going to move where x is. So this is where I let you guys play the game, is where I let people come up to the board and kind of choose the point where they think it happens. So where is the point or points where the average rate of change is equal to the instantaneous rate of change? So the things that people really pick up on immediately is that this P, this little segment that has point P on it, it needs to be parallel to the aqua looking line there, right? The slopes have to be the same is basically what we're getting at. So it looks to me this might happen possibly at 2 points here. We'll take a look. So possibly right there real quick, and then possibly right there real quick. So let's see what it says. I'm not going to hide the secant line. Let's find C. So C is the magic X value. All right, so there's one, which is kind of what I just said. And is there another one? There sure is. So it's the magic X value or values where the slope of the secant line is equal to the slope of the tangent line. And you can kind of see the visual here that these little segments that are now drawn in, they're totally parallel to the secant line. So these slopes are equal. How unbelievably cool is that? That the average, I mean, it makes complete and total sense. And then it's just beautiful. All right, so then obviously there's a bunch of, so then I would then change the function, and then we'd try it again with another one, and everyone would pretty much get an opportunity for some extra credit there, trying to find the magic point. And yes, it needs to be exact for you to get the extra credit, so it's not always available to everyone. Not everyone gets it. All right, so let's stop this. I'll just end there. I won't do any more, just to save some time here. But isn't that cool? And so this is the mean value theorem for derivatives. There's going to be another mean value theorem later in the year that hopefully we're back in school for it, and we can play the game again in person, because that one's even more fun, to be honest. All right, so we've kind of talked about what it means. We've visualized what it means. Let's talk about how this actually applies to some math here, or how we would do some problems with it. All right. So here's another picture. The slope between 2 points has to equal the derivative at some point. So there's another picture for you. Typically, questions are going to ask you to find this magic point right here, the x value where this occurs. So keep in mind there could be multiple points where the derivative is the same, and we just saw that on the sketch pad that I just showed you. So here's another example where there's 2 points, and this actually looks very similar to the sketch pad that we just had. So it's okay if it happens more than once. Mean value theorem states that there must be at least 1 point. So it could obviously be more than one. All right. So let's do an example. Find the value of c that satisfies mean value theorem for this function on this interval. So in between -3 and 4 is all that we care about here. And this is actually kind of nice because this is just a parabola. So we know it's continuous. We know it's differentiable. So what should we do first? Well, we need to find the slope of the secant line, and we need to find the slope, and we need to find the derivative, right? So let's start by finding the slope of the secant line. So I'm going to find f of 4, and I'm going to find f of -3. So f of 4, if I plug that in, what's that, 16? So that's going to be 0. And f of -3, so that's 9, plus 3 is 12, minus 12. So this one's super easy, because when I plug this into the slope formula, I'm going to get 0 minus 0 over 4 plus 3. So the slope of the secant line is 0. Okay, so I want to find the derivative should equal 0 at some point between -3 and 4. And that makes sense. This is a parabola. It's going to have a minimum, and we're looking for where the minimum occurs, actually. So it's not always going to be 0. It could be any number in the world. So let's figure out where is that point where the instantaneous rate of change, or the derivative, is equal to 0. All right, well, we can do that. Do I have space here? No. Okay, we'll do it here. So I know f prime of x. I'm so sick of this pen. All right, f prime of x is equal to 2x minus 1. So I want to know where is it equal. So I'm just going to solve quickly. So x is 1/2. So there should be a point between -3 and 4, and look at where that point is. It's totally between -3 and 4, where the slope is equal to 0. So 1/2 is absolutely on the interval. So c, I mean, you could leave it as x. I don't think you really get marked wrong with that. But the c value they're looking for is 1/2. So find the value of c that satisfies the mean value theorem. So that's what we just did there. We found the magic point where the derivative was equal to the slope of the secant line. So it's where the average rate of change is equal to the instantaneous rate of change. It's really easy when you think about it, but it's just also so cool and beautiful. All right, you try. I'm actually going to do this one with you, because I'm just going to do the whole note sheet with you, because you have extra problems to do when I'm done. So same exact idea. I need to find f of 2. I need to find f of -2 so that I can find the slope of the secant line. So f of -2, let's do it. I'll do 2 first, since that's what I wrote first. So 8 minus 24 is going to be -16. And that's going to be -8 plus 24 would be +16. Okay, so now I can find the slope of the secant line. So I'm going to do 16 plus 16 over -2 minus 2. So I'm getting 32 over -4. So the slope of the secant line is equal to -8. So that must mean, so we're continuous. This is just a cubic polynomial function. So we know that we're continuous, so MVT applies. And obviously we're differentiable. So let's do this. So I know the derivative, f prime of x, is equal to 3x squared minus 12. So I want to find the magic point where the derivative is equal to 8. So that's 4 over 3 equals x squared. Uh-oh, so it looks like we're going to get two answers here, and that is okay. And you guys know you do not need to simplify your answers. So there are 2 points, and I'll just make sure they're both on the interval. So it's plus or minus 2 over root 3. So yeah, those would both be on the interval. So both are solutions. So let's just say, let's just say one of them wasn't on the interval. That wouldn't be your C value. You would just have to give the answer that applies to the interval in question. So you always do have to go back and check that. But here they were both on the interval, so it didn't matter. Easy peasy. All right. I seem to be writing a little bit less than what's on my answer key, so I did link my answer key for you guys if you want to look at it and see everything I wrote down, but I hope I'm being clear with my explanations. Okay, so example, find the value of C that satisfies mean value theorem for f of x equals 1 over x on the interval from -2 to 2. Okay, so let's start by finding f of 2 and f of -2. So f of 2 is 1/2, and this is -1/2. All right, so I'm going to do, it's 1/2 plus 1/2 over 2 plus 2. So that's 1 over 4. So I'm looking for a point, so f prime of x, this is really x to the -1. So it's going to be negative x to the -2 is my derivative. So f prime of x is -1 over x squared. I want to know where is the derivative equal to the slope of the secant line. What's that, baby girl? Come here. You want a treat? Guys, give me 1 second. I'm not hitting pause and stopping, so I'll be right back. Come on, let me get you a treat. Actually, while I'm gone, you guys think about what could be slightly going wrong here. You want a Hershey kiss? You want a Hershey kiss? Look at what mommy has. Oh, that's for you. Okay. All right. Maybe some of you figured it out. So let's see. I want to know where is the derivative equal to the slope of the secant line. So we have the slope of the secant line is 1/4. And I want to know where is it equal to the derivative. I'm going to cross multiply. I'm going to come over here. And I get x squared is, and I take the square root of both sides and I get an imaginary answer? Why? So the value doesn't exist? There is no C value? Why, guys? Why is mean value theorem not working? Wait. Is mean value theorem invalid here? I am so confused. No. Mean value theorem is never invalid. It's not failing here. There's nothing wrong with mean value theorem. What's wrong here is that this interval, the function is not continuous on this interval, right? We know that this function does not exist at x equals 0. So mean value theorem just doesn't apply here. You can't apply mean value theorem if the function is not continuous. So mean value theorem is not failing here. It just doesn't apply here. You can't use it because the function is not continuous on this interval. MVT only works. I'll just say MVT is not failing here. The function is not continuous. She's currently getting chocolate probably all over my sofas. The function is not continuous on the given interval. There's a non-removable discontinuity at x equals 0 if you want to be specific. So MVT cannot be applied. Alrighties. So you always have to check that, guys. I obviously put that on there on purpose. So let's change our wording a little bit. And now I'm changing the interval from 1 to 3. Well, who cares that the function itself has a discontinuity? That's okay. MVT is going to apply as long as the interval in question is continuous. And the interval in question from 1 to 3 here, the function's continuous. The only discontinuity that this function has is at x equals 0. So this should be fine. So we still know that f prime of x is negative 1 over x squared. That's what we said before. And now let's find f of 3 and f of 1. So MVT should be totally fine here. So that's 1/3 and that's 1. All right, so let's find the slope of the secant line. So let's do 1 minus 1/3 and then 1 minus 3. So what's that? 2/3 over negative 2. So this is going to simplify to negative 2 over 6, which is negative 1/3. All right, so let's see. Where is the derivatives? This should work out. We should get our negatives to go away, and we shouldn't have any imaginary answers. So what I'm doing right now is I'm taking the slope of the secant line, and I'm setting it equal to the derivative to find the magic x value where this is going to happen. So I get x squared, well, I guess technically negative x squared equals negative 3. So x squared equals 3. X equals plus or minus root 3. So let's just make sure both of these answers are on the interval in question, and they're not. Okay, so we're only going to give one value here. Even though technically we got two answers, we're only worried about the interval of 1 to 3. And the answer, so we're going to give our C value, is the positive version of that. So we're not going to give both the plus or minus, just the value that is in question, because that's what's on the interval. All right, I probably went a little quickly through that, but pretty clear. The function has to be continuous and differentiable for MVT to be valid. All righties, so now comes the fun. Oh, hey there, free response question. So this is so funny that this came up today. I'm friendly with the AP Calc teacher at Cresco, and he and I were just talking about, so this is a typical table problem. You will get a table problem on the AP test. Like it happens every year. So we just call them the table problems. And part A of the table problem is always the same thing. So this is just making me giggle a little bit right now because I don't even need to read it. I know what part A is going to be asking of you, but watch it not be that. So let's see. Hot water is dripping through a coffee maker. Filling a large cup with coffee. Blah, 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 blah. Okay, so the amount of coffee in the cup is given by this differentiable function. So this is a key, right? This is very, very important. It tells us it's differentiable. So if something is differentiable, it's obviously continuous. Does it work the same exact the other way? No. So you're looking for them to tell you that it's differentiable so that you know it's continuous. Where t is measured in minutes. Okay. Hey, chocolate hands, come here. Did you wipe your hands? Oh my God, what a good girl. Good girl. Yeah, you shouldn't eat wipes. They're yucky. All right. Use the data in the table to approximate C prime of 3.5. Come here. You want another Hershey Kiss? You want another Hershey Kiss? Come here. There you go. There you go. Okay, give mommy 5 more minutes. Am I just like the mom of the year right now, just bribing my 1-year-old with chocolate? I mean, let's be serious. So we want to approximate the derivative. So when we want to approximate the derivative, we are looking for the average rate of change, okay? We're just doing an approximate, so they're asking for the average rate of change. You don't need the exact answer, aka the derivative. I mean, they're probably going to ask you that eventually, but they want to know if you know what they mean by approximate, and that just means we want the slope of the secant line. So use the data in the table. So if I want to estimate 3.5, I'm going to go right in between. I'm going to choose these two. Okay, so I'm going to say f of 3 is equal to 11.2, and f of 4 is equal to 12.8. So if I want to estimate, I'm going to use the slope of the secant line or the average rate of change. So I'm going to do 12.8 minus 11.2 over 4 minus 3. And this is a no calculator problem, so the numbers have to come out okay. It can't be anything crazy. So what's that, 1.6 over 1? Okay. Show the computations to lead to your answer and indicate units of measure. So this is another thing. This is a free point right here. Don't forget to write your units. So C prime of 3.5, my estimate is 1.6. Now let's go back and look at our units. Ounces in minutes. Okay, so this is a rate. So we're talking about the rate at which the cup is filling with coffee. So we are at this exact moment in time. So at t equals 3.5 minutes, the rate at which the coffee is increasing in the cup is 1.6 ounces per minute. Okay, let's take a look at part B. So usually it goes like up to part E, but this is all we're ready for right now, so it's still a fun question to do. Is there a time on the closed interval? Okay, so here's our closed interval, and we know we're differentiable on the open interval, so right away something's going off in my head right now. I'm thinking mean value theorem, where C prime of t is equal to 2. Justify your answer. So is there a time where the derivative is equal to 2? Well, let's do it. So let's find the average rate of change between these 2 points. So I need to find f of 2 and f of 4. So I'm going to get that from the table. That's 8.8 and 12.8. Oh, and it's even more beautiful with the subtraction. You can tell already. So this is the average rate of change. Is going to be 12.8 minus 8.8 over 2. So 4 minus 2 is 2. So I'm getting 4 over 2 is equal to 2. So look at that. Is there a time where C prime of t is equal to 2? Well, absolutely. Mean value theorem is going to apply here. So this is the slope of the secant line. So the derivative, so since it's continuous and differentiable, and we're going to have to state this in a nice sentence, we know that mean value theorem applies here, where the slope of the secant line is going to equal the slope, the instantaneous rate of change. So let's write a sentence. Okay, so since, oh, and I shouldn't be using F, guys. I should be using C for all of these. Whatever, we can go with it. So since C of t is differentiable, and you would write this out. I'm not going to write it out just for space reasons, but you're going to, you know what, I don't even set a bad example. Differentiable. Girl, what are you doing? We know differentiable on 0 to 6. We know, and notice how I used a open interval there. We know C of t is also continuous. On 0 to 6. And I'm using closed interval here because that's what was given to me over here. Therefore, MVT would apply so there must be a point I'm gonna change my color and come over here. There must be a value, a t value, where C prime of t equals 2 because the average rate of change, girl, if you break that, the average rate of change between t equals 2 and t equals 4 is equal to 2. So, I mean, I'm just writing a lot here. You wouldn't have to write this. So MVT states that, I should have just, the instantaneous rate of change must equal the average rate of change on the given interval. Okay, so that was a long sentence. If I look at my answer key, I wrote this much more short and sweet, but whatever. I got my point across and I got full credit. All right, so this is your intro to a table problem. Part A of a table problem will literally always ask you to find the average rate of change. I don't think I've seen one that doesn't. Now, watch, there'll be this one this year that doesn't ask you to do that. But, yeah, and obviously, I know I screwed up my F and my C there. Just be careful with the variables that were given to you because they kind of do care about that. So I screwed that up. So let's read my sentence one more time. Since C of t is differentiable on 0 to 6, on the open interval 0 to 6, we know that C of t is also continuous on the closed interval 0 to 6. Therefore, MVT would apply. So there must be a t value where C prime of t is equal to 2. because the average rate of change between t equals 2 and t equals 4 is equal to 2. So MVT states that the instantaneous rate of change must equal the average rate of change on the given interval. What a beautiful statement there. All right, that's it, guys. There is homework posted for you. I hope you enjoy and think mean value theorem for derivatives is as beautiful as I do. Have a wonderful weekend, guys. I don't think I see you Monday. No, I don't, but I see you Tuesday. All right? Have a great weekend, guys.